Hi folks, we're continuing on with your chapter 1. So again, if you're watching these videos, my guess is that I'm not here unexpectedly. So again, I'll say this at the beginning of every video. Even if you haven't done lesson 1.1, 1.2, you can totally do today's lesson, okay? So don't feel that you're behind or anything like that. These can be standalone lessons. So if you have your yellow formula sheet from the beginning, you'll see on it geometric sequence. And that's what we're working on today, is the geometric sequence. So a couple of things is geometric means that you multiply to get to the next number. And sequence just means finding the value of a certain term. So I want to know what the value of the 10th term is. We'd use a sequence formula. So geometric sequence is just those set of numbers that has a pattern to it. So let's do this one. 2, 4, 8, 16, 32. Oh, I went off the page, sorry. That's a geometric sequence because to get from 2 to 4, I'm multiplying by 2. To get from 4 to 8, I'm multiplying by 2. To get from 8 to 16, I'm multiplying by 2. We know that this is a geometric sequence because we're multiplying to get to the next number. Okay? An arithmetic sequence would be where we add or subtract a number. All right. Geometric sequence, multiplying the previous common ratio. Common ratios can be found by taking any term, excluding the first term, and dividing it by its preceding. Preceding just means the one before it. Okay, we did that. If you've watched the arithmetic videos, we've done that with that before. So the geometric sequence is Tn equals T1 times R to the exponent n minus 1. Okay, so this whole exponent, you have to do the math up here first before you actually apply the exponent. All right, so Tn is the value of the last term, or the term that you're looking for. T1 is the value of the first term. R is your common ratio. So the common ratio is what am I multiplying to get to my next number. So in this one up here, my common ratio was 2 because I was multiplying by 2 to get to my next number. And then n is the number of terms. So if you've done the other lessons, you're going to see that these letters mean the exact same thing. The formulas are a little different, but the letters are the same. Okay, so let's hop into example number 1. We'll make a little bit more sense as we actually do the math. So bacteria is reproduced by splitting into 2 cells, and then those 2 cells split into 4, and those 4 split into 8, and so on. Suppose you have 10 bacteria to begin with. Create a geometric formula. So that is a general formula to represent the reproduction to the nth term. All right, so we know that Tn, well, we don't know what that is. T1, we know is the 10 bacteria. The common ratio, okay, so let's write this out. We started with 1, then that splits into 2, the 2 split into 4, the 4 split into 8, and so on. And to indicate that this goes on forever, don't forget you're going to use the ellipse symbol, and the ellipse just means that it continues on and it's 3 dots in a row. You may have used it in English or texting people, but it's called an ellipse. So the common ratio, I mean, it's pretty obvious what's happening. We're multiplying by 2, but if I wanted to actually figure it out, take any term except for the first one. So I'm going to take 4, and I'm going to divide it by the term before it. So I'm going to divide it by 2. Ooh, and that's going to give me my common ratio. So 2 is my common ratio. Now, if I'm doing a general formula, you won't know this, and you won't know n either. So when we're making a general formula, we're not ever solving. We're just creating a nice, compact, simplified situation for this particular example. So Tn equals 10 times 2 to the exponent n minus 1. Now, some of you may want to multiply these two numbers together, and I will be disappointed if you do, because order of operations states we have to do the exponent first before we can do any multiplying. So this, ladies and gentlemen, is actually the answer for the general formula, okay? So that's as far as you can go. Do not multiply these together. That's not correct order of operations. That will totally screw up all of your future calculations using that. So remember, order of operations trumps everything. So even though we want to make this smaller, we want to make it tighter, we want to do the math that we can, there's no math we can do in this equation. All right, example number 2. The actual length of a photograph is 25 centimeters. So if I have a photograph here, and it's got some people in it, maybe a smaller person. Okay, there's my photograph. I know you're all pretty impressed. The length of it is 25 centimeters. Okay? You want to reduce the size of this picture. The photocopier that you're using can reduce the size to 67% of the original. What's the shortest possible length of the photograph after 5 reductions? 67%, original is 25. Express your answer to the nearest tenth of a centimeter. So it's telling me what I want my answer in. Okay, so we know a couple of things. We're trying to find the 5th term. That's what we're trying to find, because we're going to reduce it 5 times. So right away we know our n is 5. We know our T1 is what we're starting with, and the photograph is 25 centimeters to start with. The common ratio, what are we reducing it? Now it doesn't say, this tells me 67% of the original, so really every time I reduce it, it goes down by 0.67. All I did was convert a percent to a decimal. You get 67 divided by 100. And most of us can do that in our head, right? We know that all percents, the nice thing about percents is we know what they're out of. 100% is a perfect score. So now using our formula, Tn equals T1 times r to the exponent n minus 1. So Tn is what I'm trying to find. I'm trying to find that 5th term. T1 is 25. My common ratio is 0.67. You're like, Scallion, these are terrible numbers. Why did you make us use those? Because you're going to use your handy dandy calculator. I'm not expecting you to do this in your head. Okay, so here's the thing, ladies and gentlemen, is that order of operations says I have to deal with that exponent first. So I'm going to use my calculator, put that under here, so 0.67 to the exponent 4, and I'm going to use all my decimal places, because the only time we round is in the answer. So to be as accurate as possible, we have to use all the decimal places. So I'm going to times by the 25. And so T5 is equal to, and it said to the 10th of a centimeter. So that's 1 decimal place. So that's going to be 5.0 centimeters. And you're going to say, Scallion, do I need to put 0.0? That's redundant. I don't need to put it. But yes, you do, because it specifically said 1/10 of a centimeter. So you need to have something in the tenths place value. And if that's a 0, that's okay. But if it says tenths, just 5 centimeters is not accurate to the tenths place. FYI, we're hardcore on this in essentials. We're hardcore on it in pre-cal. I can't comment on applied, but if I say 1/10, there has to be a value in the 1/10 spot. All right, so that was pretty easy, nice and easy. It's just formula work. So I think that the thing that's going to trip you up is if you don't pay attention to your order of operations. Okay, so in example 3, a geometric sequence, the third term is 54 and the sixth term is negative 1,458. Determine the values of T1R and list the first 3 terms of the sequence. Okay, so I don't know T1, I don't know T2. T1, T2, T3 is 54. T4 I don't know. T5 I don't know. And T6 I know to be negative 1,458. Ooh, I just abandoned the 8 there. I started and I just, whatever. Okay, all right. So here's the thing. We're trying to find T1 and we're trying to find our R. All right, so what we're gonna do is we're gonna fake it. It's very rare in math that we fake things, but I'm actually gonna use just this part of the information that I have, and I'm gonna rename it. Every time I try to use a different color, it shows up. So I'm gonna fake it that this is my new T1, this is my new T2, this is my new T3, and this is my new T4. And the reason why I'm doing that is because I know a couple of things. I will know my new T1, I'll know my new Tn, and I know that I have 4 terms. So the only other variable in the equation is R left to solve for. That's a crappy pen. So that's R, that's what I need to solve for. So that's great because we know R is consistent throughout the entire pattern. So I'm going to use the formula. So my fake T1 is 54. So these are my fakes. T4, again, under my fakes, is negative 1,458. I know that my N is 4 because I only have 4 terms in my fake sequence. And I'm looking for R. If I know R, then I can go back to my real and solve for that. So sometimes you have to use the information given and start your sequence here instead of back here. So I'm just calling these my fakes because it's not my true, this isn't my true T1, this is actually T3. But I'm smart enough that I can use the information from here and apply it back to the original. So I have negative 1,458 equals T1, which is 54, bracket R to the exponent 4 minus 1. All right, so negative 1,458 equals 54 times R to the exponent 3. All right, this is exciting. See how much you paid attention in intro. Order of operations, I'm trying to solve for R, so I got to get rid of that 54. So I'm going to divide that 54 out on both sides. So R cubed is left there. 5 by 54. I'm going to get a negative 27. Now, to get rid of a cube, or to get rid of an exponent of 3, the opposite to exponenting something is to root it. So if I take the cube root of that, those will cancel out. And if I take the cube root of this, I can calculate it. So that leaves me with just R, and this leaves me with a negative 3. So my common ratio is negative 3. So knowing that, I know going forward, I'm timesing everything by a negative 3. Great, perfect. So if I want to go backwards, if I'm going forwards, I'm timesing. If I go backwards, I am dividing by that -3. I don't know if you can see the divide symbol. So I'm going to take my 54, and again, if the common ratio is all about going forwards, right? So I'm timesing by -3, and let's just double check that that actually works. So 54 times by a -3 gives me, I'm going to try my pink pen again, -162. It's kind of hard to see, but you can see it. Then I'm going to times -162 by the -3, and that's going to give me 486. And if I times that by the -3, I do actually get the 1,458, -1,458 is the correct answer there. So I know my 3 is right, so that's how I'm going to check it. But now I got to work backwards. So working backwards means I'm going to divide. So 54 divided by -3 is going to give me a -18. And -18 divided by a -3 is a +6. So the question asked for, find the values of T1, R, and list the first 3 terms. So T1 is 6. Let me switch back to my other pen because it's darker. T1 is 6. R is a -3. T1 equals 6. T2 is -18. Ooh. And T3, given in the equation, is 54. So I need this and this to fully answer that question. So again, order of operations is like top. It trumps everything else. And if you have, make sure you answer the question. That's another one. Simple reading, but you get caught up in doing the math. And then you forget to maybe put this part in and you lose marks for that. So just keep that in mind. Okay, so, okay, all right. So this is my question that is supposed to be for the music people, but we had to, I won't say dumb it down, we had to thoroughly explain it for us non-musical people, which would be me, so it took me a little bit. So the first key on a piano has a frequency of 27.5 hertz. And the 88th key on a piano has a frequency of 4,186.009 hertz. Okay? These frequencies follow an approximate geometric sequence. All right. So here's the thing. Let's do part A. It sounds like a lot. It sounds confusing, but it's really not. Okay, so this is almost exactly, part A is almost exactly like the question we just did. I gave you first key and fourth key. All right, the first key and fourth key. Easy peasy. So we're gonna do hertz. So we know that T1 has a hertz, a frequency value of 27.5. We know that T4, so that's your Tn, that's your last one, is 32.7. Sorry, my decimal didn't show up there. I know my N is 4, because I'm only looking at 4 keys, and I'm trying to calculate that R. All right, so we are gonna go 32.7 equals 27.5, bracket R to the exponent 4 minus 1. And we are going to divide out the 27.5 because we want to get R by itself. That's our goal, is to isolate that variable. 32.7 divided by 27.5. Sorry, I'll put this down here so you can see it. 32.7 divided by 27.5 is going to give me, and again, we want to use all those decimal places. We only round in our answer. What do you notice about the pattern here though? It's repeating. 90 repeats. So I can just put that line on top of it, but the line only goes over the 90 because that's the part that's repeating. So we've got R cubed, and we just discussed how to get rid of a cubed. We do the cube root. And if you don't know how to do the cube root on the calculator, all calculators are different. Very few of you have graphing calculators, so I'm not sure you want to watch me. But you're looking for your cubed root button, something like that. And I'm going to say answer from the other line. And this is 1.059. I think I'll round to there because it said calculate the common ratio between, we'll round to 3 decimal places. That's pretty common. There's no unit of measure here. All this is telling us is what we multiply each frequency by, each key by, to get to the next key. Okay, so I've done that. So question B says, use the highest and lowest frequencies to verify. Verify is we are verifying to make sure that we get the exact same answer that we did in A. So we know that T1 is still 27.5. This time we're going up to T88, the last key. So that's 4,186.009. We know that N is 88. That's how many number of keys I have. And I'm solving for my common ratio again. You're like, Scallion, I'm not okay with this, but you will be fine, I promise you. You're going to use a fancy button on your calculator probably for the first time. It's going to be a good day. So 88 minus 1. So I'm going to divide out that 27.5. Divide out that 27.5. 4186.009 divided by 27.5. 152. And again, we want to use all those decimal places. 5091. Ooh, I left myself approximately the right amount of room. So, okay, so we have an exponent of 87. So the opposite to an exponent of 87 is the 87th square root. And you're like, I've never heard of such a thing. But it's the same premise, it's just a much bigger number. So what you're going to look for on your calculator, what you normally have to do first is put in 87, tell your calculator what kind of root you have to do. Find your, oh, that's not where I want it to go. Let me just get to the end of 87. I want to hit math. I'm going to go down to option number 5 for me. So you're looking for something, let me go back to math for a second. You're looking for something that has x square root. And there's the index right there. The index is just a little number that tells you what kind of root it is. And we're trying to find the 87th root. So you always put, in most calculators, I should say, you always put the type of root first. And then, so I put in 87, then I hit that button. I'm going to take my answer from the above line. And that calculates the 87th root of that. So the 1.059. If you notice, if you look up here, that was my other calculation. Nice thing about this, let me put my calculator back under here. The cubed root of the answer that we did was 1.059428. And this one is 1.05946. So we're really, really close. It's not until the 10,000th place that digits separate, which is great. So we've verified that the ratio is the same here and the same here, as it should be. That ratio should not change. No matter where you are in your sequence, that ratio should be approximately exactly the same. Approximately exactly, probably not really good math terms here. Okay, the little notes at the bottom, this is like for your information and something I'm super pumped about. So the Fibonacci spiral, if you construct a series of squares with lengths of the Fibonacci sequence 1, 1, 2, 3, 5, 5, and trace a line through the diagonals of each square, it forms what we call the Fibonacci spiral. Sometimes that's called the golden spiral. And you're like, Scallion, is this going to be on the quiz? No, it's not, but you're going to be smarter people. So many examples of the Fibonacci spiral can be seen in nature, including the chambers of a nautilus shell, which is right here, that spiral. This is the inspiration for my door. This is what it's based on. It's this golden ratio here. These increasing by this pattern, Fibonacci created this pattern, and it created this beautiful, beautiful spiral. Everything is connected mathematically, and it shows up in nature. So Fibonacci was the guy who connected these two what he saw in nature, and he saw this repeating pattern. It was the same ratio every time, and it was very pleasing to the eye. So he found it, he got to name it. Of course, you name it after yourself, and that's what inspired my door. So just a little background. And all of these are sequences. There's a pattern to them, and finding patterns in math is one thing that we do really well. Anyway, that's your lesson for today. The assignment is attached. Let me know if you have any questions. Thanks.